Let's see how we use Colab to implement this simulate annealing algorithm for 2-opt. So definitely we will follow what we just derived, calculate the distance reduction from these operations. Here we add some boundary value for this distance, for this difference, is because that the range of our calculation in algorithms, in numerical algorithms, is to guarantee that the solution is within the range of the memory, which does not affect our analytical insights. So we just use our probability of the Bernoulli distribution as delta C divided by T minus under with the exponential rate. Okay, so here we can see the temperature value is given for our one-step 2-opt operation. So here, if our distance after the swap operation is improved, we will accept and then implement the swap operation, or we generate a uniform distribution and then compare it with the probability threshold of our Bernoulli distribution to generate the Bernoulli distribution. So if we randomly generate the value, so we have a small chance of e to the power of minus distance difference divided by temperature to accept the operation even the difference after the swap is positive. That means the solution is jumping from the local optimum to somewhere else. Under a high temperature, it may allow the solution jump out of local optimum to a better solution, which we hope to be a global optimum. Then we implement this one-step simulated annealing method and then iteratively adjust the temperature. For example, here we have initial temperature which can be relatively high, and then after several iterations, every iteration we update our temperature by constant cooling rate. This cooling rate is definitely between 0 to 1. And then after we update our temperature, we will keep doing our one-step 2-opt operations and then until we reach the max number of iterations. So in this particular case, we set a parameter with 2000 maximum iterations and then 200 as our initial temperature and then 0.995 as our cooling rate. Okay, and then after we plot the cost over each iteration, this is our iteration number, you can see that at first when the temperature is relatively high, chance to jump outside of a local optimum is high. And then after our temperature gradually goes down as the number of iterations increases, you can see finally the algorithm converts to a point, does not move outside of it with around 28.69. If you recall, our previous estimation based on our greedy algorithm is 27.69. So that indicates that we may not get a better solution under simulated annealing because it may jump outside of local optimum, which may be just be tracked as some other local optimum. So because this is a meta-heuristic algorithm, so we can try to rerun it. Now it's a little bit better, 27.69. This time again, 27.69. 27.69. Seems we cannot generate even better solution. Now I go back to 28, 28, 28, 27.69. So I would expect the 27.69 will be the best solution we can find using our fast algorithm. So here we only have 10 nodes, so which may not show the benefits using this algorithm. Let's see if we have 100 nodes. It's pretty dense. And then we generate a initial sequence, and we can see if we just randomly generate a TSP tour, it looks very messy and definitely is not optimum. And then we can definitely use our we can use our two-opt algorithm without simulated annealing. Let's see, after we run for around a little bit over 400 iterations, we can guess the solution, which looks pretty cool. And then the total travel distance is around 80.888. It's now 79.888, it's around 80. And then let's use our simulated annealing method. This time it gives us 81. Now this time is 80.5946. Yeah, now this time is 98.589. So this is better. So this is better than our pure two-opt solutions when we consider simulated annealing. So you can see the solution of simulated annealing as A may not guarantee that it's always good. It's just provide a chance that sometimes it's good, sometimes it's better, sometimes it's worse. So it all depends on the initial condition where you start, and then also the hyperparameters as the cooling down rate and the initial temperature setting.